Okay, so in the last class we discussed about that algebraic expression for calculating the h of n, and which will be multiplied with the w of n, and then we get that combined filter response, and then the signal will be convolved with that, and we get the desired FIR filter implementation using windowing methods. So today we talk about that frequency sampling methods. So how do we implement FIR filter using frequency sampling methods? So as you know that what is frequency sampling method? So let's say I said there is two methods of FIR filter are there in frequency sampling. One is called non-recursive FIR filter, another one is called recursive FIR filter. Let's first talk about the non-recursive FIR filter. So what is that frequency sampling method? So what is frequency sampling method? It is nothing but that the given specification of the filter is nothing but a spectrum of that filter. That means I have given design and low pass filter whose cutoff frequency let's 2 kilohertz. So let's Fp is equal to 2 kilohertz, and then I know sampling frequency, and then I know omega p. Once I know omega p, what is given to me? This one is given to me, that is the magnitude response h the omega mod, magnitude response which is given in specification. Okay? So that is given in specification up to omega p, this will be 1 and this will be 0 after omega p. That was the specification is given. Now if I do it in actual magnitude response of this filter, it will be look like this 0 and then Fs, because magnitude response is symmetry at Fs by 2. So at Fs by 2 it will be symmetry, okay or not? So that's why I get this one is omega p and this one is also omega p. So this side and this side, both side I will get. This is the magnitude response of the filter. This one is the symmetry property. So I use Fs by 2 part is sufficient. This part is sufficient, but in theory I get that entire part. Okay, so this is given to me. Now what I can do? So this axis, this is omega, or I can say this axis is f, which is normalized discrete frequency. This axis can be represented by k. The relationship is a equal to 2 pi by n in into k. So this axis I sampled. So I take a sample. Let's say I take n number of sample, here it is 15 number of sample, n equal to 15. So if I take n number of sample, then the resolution is 2 pi by n into k. So that I know. So that becomes k. So k is varies from 0 to n minus 1. So I take those sample. So instead of taking the continuous frequency response, I sampled the frequency response. That's why it is called frequency sampling methods. Okay? So I take a finite length of frequency sampling n equal to 15, maybe n equal to 64, n equal to 320. So but once I take it, and then once I take the inverse Fourier transform and design the filter, then if we draw the frequency response of the filter, it will be look like this. So that introduce some ripple due to the finiteness, introduce some ripple in the pass band, introduce some ripple in the stop band, and also introduce some transition bandwidth. So this is the symmetry property. So the signal is time domain is also. So this is the frequency response, magnitude response of that design filter. So this is the design filter, and this is the given filter. This is given by the user, and I take the frequency sampling. I design the filter. Once I draw the frequency response, I will get this one. Okay. So now frequency sampling method, I can take it due to the finiteness of that impulse response, the filter response, instead of this sharp cutoff, this is changed to this kind of things. So, how do I design this one? How do I derive this Hn? Method is very simple. That first, from the given specification, we draw the mod of H omega and then sample the omega e to the power minus j 2 pi by n into k. So, omega is nothing but e to the power j 2 pi by n into k. So, that I sample k is 0, 1, 2, 3, 4. So, 0, 1, 2, 3, 4 up to n minus 1. Okay. Then from there I compute h of n. So, h of n is nothing but the inverse discrete Fourier transform of h omega. I get h of n, which is nothing but this one. So, this is the simple methods. Now, what is the problem in here? The problem in here is one. One is called this type of sampling can be happen in two types. I sample it. So, f is equal to twice pi by n into k. Now, if the k is equal to 0, then f is equal to also 0. So, I start from 0. So, the unit circle, this is the unit circle. So, I take the sample at 0th location, then uniformly sample including start from 0th location. So, for n is equal to even, I will get this one. For n is equal to odd, I will get this one, but start from f equal to 0 inside the unit circle. Okay. So, this one is called type 1 frequency sampling filter, type 1 frequency sampling filter. So, in type 1, the frequency sampling start from 0. Then I can say instead of 0, frequency sampling can start from some little bit of offset. That is nothing but a k plus half I added. This is called type 2. So, if k equal to 0, f is not 0, f is fs by 2n. So, it starts from here. So, this is for n equal to even and this is for n equal to odd, and this is the unit circle. So, this is type 2 sample position and this one is type 1 sample position. So, when I say type 1, then I say k is k plus alpha. If I say it generalize, then alpha equal to 0. So, if this half is represented by alpha, so if alpha equal to 0, then it is type 1. If alpha equal to half, then it is called type 2. So, I can implement a type 1. So, f equals to start from 0, f equal to 0, sampling at 0 from 0. So, frequency is 0, that means including the DC, and without that DC also I can implement that filter which is fs by start from fs by 2n. So, type 1 implementation and type 2 implementation. Let us talk about how to implement it. Let us say generalized form of Hk. So, what is Hk? Hk is nothing but if h of n is my impulse response, then Hk is nothing but a frequency transform of h of n or Fourier transform of h of n. So, if I generalize it, which is nothing but a k plus alpha which include type 1 and type 2. When I say type 1, then I say that alpha equal to 0. In case of type 2, I said alpha equal to half. Okay. So, I can say the frequency response is nothing but the inverse Fourier transform, but k is equal to k plus alpha. K is replaced by k plus alpha. So, basically hk plus alpha is nothing but the what is the resolution? 2 pi by n into k plus alpha, that is the frequency f or omega I can say, this is h omega. So, h k plus alpha is equivalent to h omega which is sampled at 2 pi by n. Is it clear? Now, this is the equation number 1. So, in equation number 1, if I multiply both sides with e to the power j 2 pi by n, n into k plus alpha, and take the sum over k equal to 0 to n minus 1. So, this part extra I am writing. So, I am writing in this side, and this also you will write in this side also. So, I write in this side also. Now, if you see, this one is equal to this one and this one will be cancel each other. So, which is nothing but a n equal to 0 to n minus 1 h of n. So, what is there? N equal to 0 to n minus 1 h of n, which is nothing but a h0 plus h1 plus. So, if all are 1, it is nothing but a n. So, if it is n, then I can say h of n is equal to 1 by n into this one. So, now if the alpha is equal to 0, this is nothing but a simple inverse DFT, I DFT. If it is alpha not equal to 0, then also I can calculate. So, what is my intention? My intention is that I have given that h omega is given by the user. I frequency sample that h omega, and from there, which is nothing but a hk plus alpha, depending on the implementation, I can say if it is type 1, the straightforward alpha is equal to 0, and I can calculate that h of n using inverse Fourier transform. So, idea is very simple, that I have the specification is given, the magnitude, the spectrum of the filter is given. What is spectrum? Y axis is the magnitude, x axis is the frequency. Now, this is symmetry. So, if I know that any discrete Fourier transform, as you know that any discrete Fourier transform is symmetry, that this is 0, this is n. So, I know n by 2 point symmetry. So, if this is my filter response, this will be repeat in here also. So, from there I sampled it. So, it is nothing but n number of sample. So, it is 2 pi by n is the sampling, the resolution of the, then I take the number of samples. So, n number of sample I have collected, and once I collected the n number of sample, I take the inverse discrete Fourier transform, I get Hn in case of type 1. In case of type 2, instead of inverse discrete Fourier transform, I am doing the same convolution, but with the alpha value. Alpha is equal to half. So, my ultimate objective is to find out h of n. Once I get h of n, then I know yn is nothing but a convolution between h of n and input signal x of n. So, given specification of the filter, I have to find out the frequency response of the filter, and from frequency response I have to sample that frequency response, and I have to find out the impulse response of the finite impulse response of the filter, and once I get the impulse response, I just convert with the input signal, I get that output of the filter. So, if I do that, the mathematics, that what I should do, that since Hn is real, then I can say hk plus alpha is also symmetry. So, which is in complex domain, hk plus alpha equal to h star n minus k plus alpha. But when I said the mod domain, it is nothing but a h of, so I can say I know h of k is mod of h of k is equal to mod of h of n minus k. That's I know from the symmetry function. And in case of complex domain, it is nothing but a complex conjugate. So, you know if it is H0, then I know it is nothing but a H of complex conjugate of H0 is H of minus 0 star. So, which is nothing but a H of n star. So, if this is A plus JB, this will be A minus JB. The complex conjugate, that I have given an assignment problem also this step. Okay. So, since that amplitude response or the magnitude response is symmetry, so instead of, so when you do the frequency sampling, you take the entire filter and n minus 1 number and you collect the sample. So, instead of that I can take only simple n by 2 is sufficient, this portion I do not require. So, when I do the inverse DFT I can simply take the n by 2 point is sufficient. So, n by 2, n may be a odd or n may be a even. So, in case of n even I can take n by 2, in case of n odd I just n plus 1 by 2 point sufficient. Okay. So, how do I calculate the maths? If you see h omega is equal to this one we have already said that that symmetry and anti-symmetry property of the filter we have derived the linear phase condition. If I took the linear phase condition, this is the generalized equation of the frequency response of the filter. Now, I make it more generalized in sampling domain, taking instead of pi by 2 I take beta pi by 2. So, beta is equal to 0 means symmetric and beta equal to 1 means anti-symmetric. So, this is the equation of an anti-symmetric frequency response. So, if I multiply with beta, so beta is equal to 0 means it is symmetric. So, this portion will be not there and beta equal to 1 means it is anti-symmetric filter. And HR omega is nothing but a sampled at 2 pi by n k plus alpha. So, alpha is equal to 0 means type 1 and alpha equal to 1 means type 2, alpha equal to half means type 2. So, if I derive that equation, let us say of real frequency sample is given g k plus a. So, real frequency sample is given g plus not a, it is alpha. So, insert symbol problem. So, alpha. So, I can say g k plus alpha is equal to k to the power minus 1 h r this one. Now, minus 1 to the power k, what is the meaning? E to the power j pi k. So, I replace by e to the power j pi k and replace this g k plus 1 in this equation. So, I get this one. So, what will be given? So, g k plus alpha is nothing but a given specification of the frequency response of the filter. Let us an example, let us say I took you first example, then let us the given specification is given this one. HR 2 pi by n into k is equal to, so k equal to 0 means, so HR 2 pi by n 0 is equal to 1. So, that means HR 0 is 1 and HR 2 pi by n is 1, HR 2 pi by n into 2 is equal to 1. So, if you see, if I say m is equal, order of the filter is 17. So, 17 is the odd. So, 17 plus 1 divided by 2. So, I required 18 by 2. So, I can say 9 number of impulse frequency response I required, 9 samples I required. So, those are the 9 samples given. Rest 9 I can generate. I know it is nothing but a complex conjugate. So, if it is real, it is same. So, next portion will be the same. So, once I know this, I can implement this type 1 and type 2 filter. How? So, I have to, so gk, so this one I know. So, gk is nothing but a minus 1 to the power k, or I can say this one is minus 1 to e to the power j. So, I can say that this is given. So, I can multiply this one and I get this one. Okay. Then I have to calculate h of n. So, how do I calculate h of n? So, there is a two condition. One is alpha is equal to 0, one is alpha equal to half. This one is type 1, this one is type 2. And for symmetric condition, so symmetric means h of n is equal to h of n minus 1. That is the symmetric requirement. So, if the symmetric requirement, I can say gk, so alpha is equal to 0, so it is becomes gk minus 1 to the power k, h are this one, and I can say gk is equal to minus g, and this is the symmetry. So, if you see that if hk is a symmetry, hk plus alpha is a symmetry, then gk plus alpha also symmetry, the same frequency response. So, I can say gk is equal to minus gn minus k. Then I can, if I derive that equation using that linear phase filtering methods which I described in, I think, lecture number 2. So, if I put that equation, I get this is the impulse response of type 1 alpha equal to 0. So, u equal to n minus 1 by 2 for n odd and u equal to n by 2 minus 1 for n even. Similarly, for alpha equal to half, this one, and I can derive this equation from there. So, you can try derive in your home, try to derive this equation using mathematics, or you can directly use this equation to derive h of n. Okay, for symmetric condition. Then what is for antisymmetric condition? If it is antisymmetric, again alpha equal to 0 and alpha equal to half. So, for alpha equal to 0, this is my equation for n odd and this is my equation for n even. For alpha equal to half, this is my equation for n odd and even. For this is the extra things I know. For antisymmetric, n odd means g n by 2 is equal to 0. I am considering this one. I get this one for n odd and n even. Now, let us, the problem is given like this. So, what is the problem? Is determine the coefficient of a linear phase FIR filter of length m is equal to 17, which is a symmetric unit impulse response. Symmetric means h of n is equal to h of n minus 1. So, I know this condition number 1, symmetric condition. So, and alpha equal to 0. So, what is given? Alpha equal to 0. So, h r 2 pi by n k plus alpha is equal to 0. So, I can say this is nothing but alpha k is equal to is given. So, this is given to me. Now, I have to find out h of n. So, which condition I will apply? I will apply symmetric alpha equal to 0. Then I know h of n is equal to 1 by n. So, I know how to calculate h of n. So, I know that equation. So, here I put equation. What is gk? Gk is minus 1 to the power k into hr 2 pi k by n. So, this is 2 pi k by n. So, what is gk? Gk is equal to minus 1 to the power k into hr 2 pi n by k. So, I can say k equal to 0. G0 is equal to minus 1 to the power 0 hr 2 pi by n into 0, which is equal to 1. So, I can say this is 1 into 1 is equal to 1. What is G1? I can say G1 is equal to minus 1 to the power k means 1 into hr 2 pi by n. So, that is my G1. So, I know G0, G1, then I can calculate h of n. So, h of n is odd or even? N is what I given? N is equal to 17. So, I use this equation, n is equal to odd. So, I can say u is nothing but n minus 1 divided by 2. So, I can say h of n is equal to 1 by n G0 plus. So, G0 is nothing but a 1. So, then I can calculate this one where n is equal to 17. So, once I get h of n, how many h of n is required? So, if I calculate h of n, let us I take that equation. This is given where n is equal to 17 odd, and I get this equation. I know u is equal to n minus 1 divided by 2. Now, I am calculating h of n using this equation. So, h of 0, h of 1, h of 2, h of 3. So, how many, what is the length of h of n? H of n is varies from 0 to n minus 1. So, it is nothing but a 0 to 17 minus 1. So, 0 to 16. So, index of n up to dot dot h of 16, okay or not. So, now I know h of n is also symmetric. So, h of n is equal to h of n minus 1. So, I know h of 0 is equal to h of 17 minus 1 minus 0. So, which is nothing but a h of 16. So, I do not have to compute h of 16. I know if I compute h of 0 which is equal to h of 16. Similarly, h of 1 is equal to h of 17 minus 1 minus 1. So, which is nothing but a h of minus 2, h of 15. So, h of 0 is equal to h of 16, h of 1 is equal to h of 15, h of 2 is equal to h of 14, h of 3 is equal to h of 13. So, so I do not require to compute all n minus 1 number of h. I only have to compute n minus 1 by 2 number of h. Is it clear? So, I do not have to compute all the hn. I do not require. So, I compute this hn and then I repeat it that side. I know this is a symmetric filter. Compute that h of n is given. So, once I know the h of n, I can compute y of n. Y of n is nothing but a convolution of h of n with x of n. If I want to know after design what is the frequency response of the filter. So, I have given that filter. If you see k equal to 0, 2, 1, 0, 1, 2, 3, 4. So, for k equal to 4, I have given, I take another slide here. So, up to k equal to 4, it is 1. So, what is the what kind of filter I have given? I have given this side is k. So, up to k equal to 0, it is 1, 1, 0, 1, 2, 3, 4. Up to k equal to 4, it is 1, and then it is reduce, like that kind of things I have given. After that, it is 0. After k equal to 8, n by 2. So, n by 2 means n plus 1 by 2. So, it is k equal to, so k, if I say n equal to 17, so what is the symmetry? N is equal to 17 plus 1 divided by 2 is equal to 8. So, at k equal to 8, it will be symmetry. This is n. So, I can do that. So, I know that, and then I calculate h of n. So, once I do the h of n, then if I take the discrete Fourier transform of h of n, if I compute h of k using n equal to 0 to n minus 1 h of n e to the power minus j 2 pi by n into nk. Using this formula, if I compute hk, then if I plot mod of hk this side and this side is k, I get back this same or not? I will not exactly get back the same, because it will introduce some ripple because of finiteness of the impulse response. So, I will get like this. You can test it. Take an example, do it and test it. To reduce the complexity, you can take n is very small. Then there is another method I said. So, it is non-recursive implementation using frequency sampling. Now, if I go for the recursive frequency sampling filter, so in these recursive methods, what we do, we method the DFT sample Hk for FIR sequence can be regarded as a sample of the filter Z transform. So, what is given? So, I have a filter Z transform, Hz is given, or I can say that from given Hk, I want to find out what should be the possible Hz. Once I know the Hz, I can easily implement it using discrete structure 1 or 2 methods. So, what I want to know, for a given Hk, given frequency response I sampled it, and then from sampled frequency response I try to find out Hz. That is my problem. So what is Hz? Hz is nothing but a Z transform of the impulse response H of n. So if H of n is the impulse response of the filter, and that Z transform is nothing but if I take the Z transform, I get H of Z. So H of Z is n equal to 0 to n minus 1, H of n Z to the power minus n. Now what is H of n? H of n is nothing but an inverse Fourier transform of H of k. Okay or not? So here Z is equal to what? J e to the power pi by, so what is the sampling frequency? 2 pi by n into k. That is the sampling frequency domain. So it is nothing but a 1 by n k equal to 0 to n minus 1 H of k e to the power, this one inverse Fourier transform. H of n is the inverse Fourier transform. H of n is the inverse. If I know H of k, then if I do IDFT, inverse discrete Fourier transform, I get H of n. So if this is the inverse IDFT of H of n into Z minus n. Now if you see, there is a two sum, n equal to 0 to n minus 1, k equal to 0 to n minus 1. If you take the two sum, then n is constant. So I take, so n, capital N doesn't depends on small n. So I can say that I can take this sum first, and a capital N is outside, and Hk doesn't also depends on n. So I make it outside, inside the sum of k, and then sum of n depends on this one and this one. So this one and this one I write whole to the power n. So a to the power n is nothing but a 1 by a to 1 minus a to the power n divided by this one. Okay. Now if I see e to the power minus j 2 pi k, there will be, I think there will be an n also here. So 2 pi k n is nothing but a, told me, 1. Integer, all are integer. So it is nothing but an 1, j cos theta minus plus j sin theta. So all are 1. So I can say it is 1. So I can put this is 1. So this is nothing but a 1 minus z to the power minus n. So I can say 1 minus z to the power minus n doesn't depends on k. So I put it outside. N doesn't depends on k, put it outside. Then I said k equal to 0 to n minus 1 h of k divided by 1 minus e to the power j 2 pi k by n into z to the power minus 1. So this is my Hz for a given Hk. For a given Hk, this is my Hz. Once I get my Hz, I can implement it using discrete structure 1 or 2, doesn't matter. So this way I can compute Hz. So this is called recursive frequency sampling filter. One is non-recursive, type 1, type 2, I can implement Hn, here is recursive. Is it clear? So this way I can implement frequency sampling methods for FIR filter. So first I have explained, what I explained? Window methods. Using algebraic function, I have calculated h of n, I can multiply with Wn, and then I can convert with x of n, get the filter output. So I can write a program for h of n, then I can multiply Wn with the h of n, and then I can convert with x of n, get the yn. Similarly, frequency sampling methods, whether I use non-recursive or recursive, if the recursive I have to find out h of z and realize h of z using discrete structure 1 or discrete structure 2. Now once if I go for non-recursive type 0 or type 1, I can implement type 0, I can implement type 1. Type 0 means alpha equal to 0, type 1 is alpha equal to 0, and type 2 is alpha equal to half. So, whatever I can I can want, I can implement, I can find out the h of n. Once I get that h of n, I directly convert with x of n. So, here windowing is not there. In frequency sampling method, we are not doing windowing, but in window methods, we calculate h of n from that algebraic expression, then we multiply by w n and then convert with x of n. So, what I will suggest you, please implement it for windowing method and for frequency sampling method at least one, then you understand how to implement FIR filter. If you just write a MATLAB program FIR filter, FIR and then give the parameter, now you know what are the parameters also, that once you know the filter design, at least you know what are the parameter you have to provide it for FIR filter design. Okay. And next week what we will do about, let us say optimization method. Let us say ripple is given, passband ripple is given, stopband ripple is given, transition bandwidth is given. So, how do I design in optimal methods, that I will cover in the next week. So, this week what I said, the windowing methods, frequency sampling methods, and what is the filter specification, I have said that. So, summarization is that this week we learned how to specify a FIR filter, or how to specify a filter, what is linear phase filter and how do we implement the linear phase filter. Then I talk about the FIR filter. So, how to implement FIR filter using windowing methods and frequency sampling methods. In windowing methods, I know that the stop band ripples depends on the window, which window I should use, and the transition bandwidth, if I want to decrease the stop band ripple, then I have to increase the transition bandwidth. So, optimization is based on that which window I am using. Then I can use the frequency sampling methods and I can find out what is the transition bandwidth is coming out, and that frequency, then what I want to know, what is the optimized value of order, so that it will restricted with stop band ripple, pass band ripple and transition bandwidth. So, optimum FIR filter design I will cover in the next week. Okay? Thank you.